Greetings, my name is Daniel Stolfin from the University of Luxembourg. I am going to present my research work, Improving Pheromone Communication for UAV Swarm Mobility Management. This talk is divided into 4 main sections. First of all, in the introduction, I will talk about UAVs and their applications. Then, I will describe our pheromone-based mobility. In third place, I will present our optimization approach, and finally, some experimental results and conclusions. Unmanned aerial vehicles, which are also known as drones, can be multi-rotors, as quadcopters, or fixed-wing devices, having each class its own advantages and disadvantages. These flying devices are usually equipped with video cameras, radio, and variety of sensors and actuators. The use of UAVs represents several advantages for the society, although there are some concerns about drones disturbing the privacy of individuals by flying above them and monitoring their activities. UAVs' main advantages are the ability of exploring different areas, flying at relatively high speed. These eyes in the sky present also an excellent communication range, and usually there is a clear line of sight between devices. On the other hand, the flying time is short, although it is longer in fixed-wing drones. They cannot carry heavy payloads and lack of stability in harsh weather conditions. Proposed UAV applications are good transportation, including delivered pizza at home, road traffic surveillance, firefighting, environmental monitoring, wildfire monitoring, farming, monitoring crops, but also scattering seeds, architecture surveillance, internet delivery, homeland security, to herd a flock of birds away from an airport, and of course, surveillance systems. Our surveillance approach involves the use of multi-swarm of UAVs which follow unpredictable trajectories. The objective is maximizing area coverage while spotting all the intruders. For doing this, we use a mobility model based on pheromones. Additionally, in this work, we analyze other 2 mobility models. CHROME, which presents trajectories which are pure chaotic, CACOC, which combines CHROME with virtual pheromones, and our improved CACOC, named CACOC Plus, which customizes CACOC by adding a set of parameters. CHROME, Chaotic Rossless Mobility Model, uses the value of the thunderstorm map from a chaotic attractor and a decision variable to select the next movement direction. CACOC, Chaotic Ant Colony Optimisation for Coverage, works as CHROME when no pheromones are detected in the UAV's neighborhood. On the contrary, these pheromones, when present, work as repellers, moving the UAV away from the recently visited areas of the map. Consequently, virtual pheromones are useful to avoid visiting the same spot very frequently and in the short time. As pheromones eventually evaporate, those spots are likely to be visited again. We have paid attention on the pheromone trails to improve the original CACOC, using parameters to get, as a result, CACOC Plus. In CACOC Plus, the amount of pheromones left by each UAV are parameterized, as well as the scanning depth, or better, the pheromone detection range. But the pheromone map is not centralized. Although each UAV knows its own pheromone maps at any time, radio communications are needed in order to know about the pheromone maps from the other UAVs. In these examples, we can see the full pheromone map in a scenario of 2 UAVs. In figure B, the UAV 1 knows its own pheromone map and the portion of the transmitted pheromone map from UAV 2. The same in figure C. this time from the point of view of UAV2. Radio links can be subject to interferences. There is a maximum range which also affects the power of consumption of the onboard radio device. Using shorter radio packets could improve communications, but could we keep a good coverage rate by optimizing the parameters of CACOC Plus? We propose 4 scenarios to be simulated using Argo's multi-physics robot simulator. Each scenario is made of 100 by 100 cells, and we test 4 neighborhood sizes. Each UAV will transmit the complete pheromone map. 441 cells, 121 cells, and in the last one, where no pheromone maps are to be shared between UAVs. So the parameters of CACOC Plus are going to be optimized in these 4 different scenarios, also testing different numbers of UAVs. The selected optimization algorithm is a genetic algorithm, which is an inefficient method of solving high-dimensional problems as ours. We have used binary tournament as selection operator, a uniform crossover operator, a probabilistic mutation adapted to integer numbers, our parameters, and finally, after evaluating the new offspring, the replacement operator selects the fittest individual to replace the worst one in the former population. The problem representation is a vector of integer values, which are the parameters of UAVs. And the fitness function is calculated as the proportion of explored cells in the surveillance scenario. We evaluate each configuration using the Argos multi-physics robot simulator. It allows us to simulate the UAV's dynamics using a realistic communication layer, including noise and packet loss rates. We performed 30 runs of the GA per scenario, 1000 evaluations per run, which took about 10 equivalent days of computation time. These are the results of the optimization process, where the optimal parameters for CACOC Plus were calculated. We can see that despite the maximum values shown, the values achieved for each case study, sharing different amount of pheromones between UAVs, are quite similar. This indicates that the parameterization done adapted CACOC Plus to different situations without losing much area coverage. Indeed, if we now compare CACOC Plus with CACOC and Chrome, we can see that CACOC Plus has improved the other mobility models in all the tested scenarios. The optimization of its parameters allowed CACOC Plus to deal with incomplete pheromone maps. We can see that CACOC has problems to cope with communication restrictions. And finally, Chrome has its own limitations since it lacks of pheromones. A last study included the test of different packet loss for CACOC Plus. We can see that before having a notable decrement of the area coverage, the collision avoidance algorithm failed, which was more evident when there were more UAVs in the scenario as expected. We have analyzed the effects of the communications in our pheromone-based mobility, optimized it, and compared the result against 2 other mobility models for UAVs. We have observed that CACOC Plus stands out from the other models as it was able to adapt its parameters to cope with communication restrictions. As a matter of future work, we would like to use more UAVs as individual parameters. We are designing a different collision avoidance algorithm as it has shown issues facing imperfect communications. And finally, we would like to test our proposal using real UAVs. Thank you for your attention. If you have some question, I am glad to answer them here or by email.